make smaller components in AZ91D in magnesium, and if I make a larger component, I move into the cold chamber realm. And that really has to do more with the size of the equipment that's available and the pressures that I require to actually fill that component. So the advantage is really when I look at a hot chamber machine is now I can control that metal temperature a lot closer. I don't lose as much heat as I fill that mold, and so that allows me to fill thinner sections and make smaller, more intricately designed parts. I get nicer surface finishes. I also automatically refill the shot chamber every time, and so I don't have to worry about having an extra robot for controlling ladles or anything along those lines. And then the final big advantage of hot chambers is I have less oxidation. Our metals try to oxidize as soon as we melt them, and so I get a skim of scummy metal on the top called dross. And in a hot chamber machine, I tend to not have any of that dross actually showing up in my castings, which can give me a slightly better casting finish as well as better properties. And so very quickly, I see we have a couple questions coming in, and I just want to see if I can answer some of these questions. It looks like we have some questions coming in about how the presentations will be distributed afterwards, and actually we have Athena Catlett on the line who's actually going to be answering those. And so we're going to continue to move on, and we're going to start talking about our die casting dies. So we've just talked about the arrangement of the machines. Now we're going to talk about what the die actually should look like. And so typically we can do dies in a couple of different fashions. We can do a single cavity die where I make one casting at a time, or a single part per casting. If I look at a multiple cavity die, I can make many of the same parts. And so if you've done any work with, say, electrical conduit, those nuts that you use to connect all the conduit are typically zinc die castings, and they make hundreds of those per casting. So that would be an example of a multi-cavity tool. And then I can also have a family tool, and a family die is where I make two different components. And this is normally quite nice, especially if I need to have one small piece and one big piece, and they actually eventually get bolted together. I can cast both of those in the same die, and I can avoid having mismatched production volumes. I can also use a unit die, and in a unit die what I do is I make it so I can just switch out specific cavities, and so I can speed up my setup time. And so when we start looking at our die casting process or designing, we want to keep this in mind. You know, if I'm designing a connecting rod for a small engine, I'll be thinking I want to build this as a family tool because there's going to be two pieces there, and I don't want to have to balance those production volumes. And so once we pick what kind of tool we're going to make and how many parts we're going to make in that tool, we really have to figure out, we have to pick the right machine. We have to design the process. And so there's really two halves to a die casting machine. One is the injection side, and we're going to talk about this one first, and the other is the clamping side. So if you can imagine this, what I have outlined in red here on this schematic of a die casting machine is actually my injection mechanism, where the mechanism I use to create the high pressure and the high flow rate, which is going to fill that die cavity. And there's a way that I can decide how big that injection system should be. There's some critical variables I got to balance: the hydraulic pressure in the machine, the cylinder size of that injection cylinder, the dry shot speed, or how fast that cylinder can actually move when it's unrestrained by metal, the area of the gate or the nozzle that I use to fill the die cavity, the part volume or how big the part is, as well as how fast do I have to fill that part, or the fill rate or fill time. Now there's a tool we use in die casting called PQ squared, and what this does is it allows me to look at all these variables in one simple chart like you see right here. And this is very useful for you to use. And so if you're working with a die caster, what I would suggest is that you ask your die caster about PQ squared. If you're not quite sure you have the right size machine, say, hey, can I look at a PQ squared diagram? Could you explain to me what's going on here? And this is a great tool that we can use to very elegantly understand whether or not the machine will work. Now the other half of the machine is going to be the clamping side, and this is how we size our machines. When I say an 800-ton machine, I'm saying that machine can apply 800